In this video, we're going to look at both Taylor and Maclaurin polynomials. And if this is the first time you're seeing my face, hi, my name is Dr. Marissa May, and I'm on a mission to help students feel confident in their math classroom. This video is just one of the resources that I provide students to help them do that. So if you're in need of resources to help you, feel free to hit that like and subscribe button. That way you get a notification every time a new video is posted. Let's jump right in. So we know that a Taylor polynomial has a pattern. And so we look at that pattern and notice that it is centered about a value c. So we have the function, then we have the first derivative. Do you see the second derivative over 2 factorial? We would have third derivative over 3 factorial, fourth derivative over 4th factorial. And then I want you to look at the pattern with the x minus c's. So in this term, you don't have an x minus c. Then this one, you have an x minus c, then an x minus c to the second. Then the next one would have an x minus c to the third. You get the idea, right? And that's what we call an nth Taylor polynomial. So maybe we would tell you to do a third degree Taylor polynomial. And of course, it is centered about some value c. It's named after Brooke Taylor, an English mathematician. Now, if we happen to center about 0, so the same patterns apply, right? Function at 0, first derivative at 0, then x minus 0, right? And then I've got second derivative over 2 factorial, and then x minus 0 squared, so forth. That we call a Maclaurin polynomial. If it's centered at 0, then we call it specialized as Maclaurin. And it's named after another English mathematician, Colin Maclaurin. Now, these polynomials are used frequently with transcendental functions like e to the x and ln of x and trig functions, sine of x and cosine of x, to get approximations for them. So let's take a look at putting together a Maclaurin polynomial first. We're going to do a 4th degree, and we're going to do it of e to the 4x. So in general, when we have a Maclaurin polynomial, we're going to do a 4th degree, and we're going to set it up as f of 0 plus first derivative at 0. And I'm going to leave space because I'm going to come back and put the other ones here in a minute. So you can see third derivative at 0, and then, and we'll just put a 4 here. Okay, so that takes care of my function and my derivative. Now let's put in the x's. So I would have x to the 0. I'm not going to write that. Then I have x to the first. Then I have x to the second, x to the third, x to the fourth. Okay, now I'm going to build my polynomial specific to this function. So let's think about e to the 4x. Okay, so I'm going to need f of 0. That would be e to the 4 times 0, which is 1. Then I'm going to have to do the derivative. First derivative would be 4 e to the 4x. And then if I put in 0, that would just give me 4. Second derivative would be 16 e to the 4x. And if I put in 0, that would give me 16. Third derivative, that would be 64 e to the 4x. Think of chain rule. And if I put in 0, I would get 64. And then fourth derivative, I would get 256 e to the 4x. And then put in 0, I'll get 256. Now let's put these values in. So now my Maclaurin polynomial would be 1 plus 4x plus 16 over 2 factorial. I'll deal with the factorials simplifying here in just a second. Then plus third derivative, which is 64 over 3 factorial, x to the third, plus fourth derivative, which is 256 over 4 factorial, and then we would have times x to the 4th. All right, now let's think about factorial. Remember, factorial means to take the number and multiply by every number smaller than. So this would be 2 times 1. This would be 3 times 2 times 1. This would be 4 times 3 times 2 times 1. Okay, so my final answer, my Maclaurin polynomial would be 1 plus 4x plus 8x squared. Okay, 64 over 6, we can reduce by 2. That's going to give me 32 thirds x cubed plus, looks like I've got 24 there. I think we're going to be able to reduce by, so 8 here. So if we divide by 8, I'll get 32 thirds again, x to the 4th. Now, the whole idea of the approximation is the more terms I put in the polynomial, the closer and closer this polynomial equals the values of this function. Now, you may be saying, big deal. Why do we need that approximation? Well, we don't for a function just like this one, but as we get more complicated functions, then a polynomial becomes a lot easier to deal with than a very complicated function that we may or may not be able to differentiate or integrate. Now, let me do one more example, and that is the Taylor polynomial. So the setup is very similar in this one. We want a 4th degree, but the difference in this one is, of course, we're going to center at 1, we're told, okay? And so when I set up my Taylor polynomial, I've got all the same derivatives set up with the factorials. Oops, 1, sorry about that. I was thinking 3 factorial plus 4th derivative at 1 over 4 factorial. But now when we put in the x's, we have to center. So we have x minus 1 and x minus 1 to the 2nd. And x minus 1 to the 3rd, and x minus 1 to the 4th. Okay, now let's come over to the side and find our derivative, our function. So my function at 1, ln of 1 is 0. My first derivative of ln would be 1 over x, and if I plug in 1, I'll get 1. My second derivative would be negative 1 over x squared, and if I plug in 1, I'll get negative 1. My third derivative would be 2 over x cubed. And if I plug in 1, I'll get 2. My fourth derivative would be negative 6 over x to the 4th. And if I plug in 1, I'll get negative 6. So let's put these values in now. So my Taylor polynomial, and again, it's a Taylor because I'm centering at something other than 0. I'm going to put in my function 0 plus my first derivative, which is 1 times x minus 1 plus my second derivative, which is negative 1 over 2 factorial times my x minus 1 squared plus my second derivative, which would be negative 1 over 3 factorial times x minus 1 cubed plus my fourth derivative, which is negative 6 over 4 factorial. And then again, we're going to multiply by x minus 1 to the 4th. All right, just a little cleanup needed, and then we'll have this Taylor polynomial. So the 0 is not necessary to write. So we'll start out with an x minus 1. You can put it in parentheses if you want or not. It doesn't matter. Then I've got minus 1/2 times x minus 1 squared minus 1/6. I want you to think of that 3 factorial as 3 times 2. So minus 1/6 x minus 1 to the 3rd. And then 4 factorial is 4 times 3 times 2. That's 24. So if we reduce that, we'll get minus 1/4 x minus 1 to the 4th. And the last thing here said, okay, now use this to approximate ln of 1.1. So notice that that's letting x be 1.1. And so what they're saying is, hey, go ahead and plug in 1.1 for these x's. and see what you get for your value. Is it going to be exactly the value you would get for ln of 1.1? No, but it will be close. And so let's plug that in our calculator and see what we get. And for this approximation, I get that it is about 0.095. And again, remember the benefit of a Taylor or a Maclaurin is that if we get a function that is difficult to integrate or difficult to differentiate, using the approximation polynomial of a Taylor or Maclaurin helps us quite a bit. Well, thanks for watching. I hope this helped. Have a good day. Bye-bye.